How would I teach a robot to tie a shoe? Computers are good at doing exactly what you tell them to do, which is both a blessing and a curse. If I want to add two very large numbers, that's perfect. The computer can do that. But if I want a computer or robot to do everyday tasks like tie a shoe, fold a t-shirt, or even just walking, it's impossible to specify exactly how to move its joints and interact with the environment, and exactly what the forces, masses, and friction of the physical world are. Reinforcement learning is a field of machine learning that tries to solve precisely that. It's quite appealing to people because of how it resembles the way that humans and animals learn in the physical world, through trial and error and using positive and negative reward to reinforce the behaviors that you want and punish the behaviors that you don't want. In recent years, some of the achievements of reinforcement learning include learning to play Atari games in 2013, defeating top human Go players in 2016 with AlphaGo, defeating professional Dota 2 players in 2018 with OpenAI 5, solving a Rubik's Cube with a robot hand by OpenAI in 2019, certain applications in robot dogs, self-driving, fine-tuning language models, etc., and all those AI learns to YouTube videos, of which I have made one as well. This video is over an hour long, very dense in information, and not very entertaining. Its purpose is to help those who are interested learn as much of reinforcement learning as possible, as easily as possible, and as fast as possible. This is because I think that this technology and field of study will be very important in the next few decades, when artificial intelligence gradually brings its capabilities to the physical world, and I want to make the knowledge as accessible as possible to all people. We will go over much of the foundational theory and math, while demonstrating it in practice with a series of example tasks that gradually increase in complexity. That will be the bulk of the video, and then following that, we will cover the interesting correlations between reinforcement learning and neuroscience, and how the brain works. And then we will talk about the aspects in which reinforcement learning is still lacking, and some of the directions of future research that I think will be of great help. This video is not meant to be watched just once, so feel free to re-watch it as many times as you need to extract its value. The prerequisite knowledge of this video includes maths up until basic calculus and a basic understanding of neural networks. In order to research for this video, some of the main sources of information I used include the book Reinforcement Learning: An Introduction by Sutton and Bartow, which is widely regarded as the holy bible of reinforcement learning, the OpenAI Spinning Up website, which has compiled a lot of information about the most famous and influential algorithms, large language models such as ChatGPT, which are really good at searching for, compiling, and summarizing widely known knowledge, and the reinforcement learning subreddit, where you can read through other people's questions and answers on the topic. As well as these resources, I'll leave a link to some of the interesting articles that I mentioned in this video in the description. Now, before we begin, have a look at my hair. I've chosen to film the introduction at the very end, and throughout the different segments of the video, you'll notice that my hair has grown quite a bit. Indeed, this video was approximately half a year in the making, with even just the filming spanning several months. And no, I didn't avoid haircuts just to prove a point, I was just lazy. But if you watch through the video and find value in it, consider supporting the channel on Patreon, link in description. I've put some of the behind the scenes demo videos on there as of now, but those are in this video anyways. So consider supporting if you're interested in topics related to AI and robotics, and you'd like to see behind the scenes of future videos. With that being said, let's get started. In reinforcement learning, which I'll refer to in the rest of the video as RL, there is an agent and an environment. Agent is the car, environment is the road. Agent is the player, environment is the map. Agent is the hand, environment is the cube, and agent is the strategy, environment is the chess match. The definition of agents and environment, which generalizes to all these situations, is that We can say the agent is whatever you can directly control, and the environment is whatever you cannot directly control, but you're trying to indirectly interact with through the agent. Now, when the agent interacts with the environment, obviously there's two directions of influence. Influence of the agent on the environment is called an action. And as a human, you can intuitively think of the movement in your limbs and your muscles. Influence of the environment on the agent is called state. And as a human, it's your sensory input. You're observing the state of the environment. As a human, the sensory input and motor output loop is kind of like a form of this agent-environment interaction, where the brain is the agent, responsible for integrating data and decision-making. In RL, we're trying to create such an agent, such a brain, using a computer. So of course, all these states and actions have to be represented as numbers. The state could be position and velocity, colors of pixels, temperature, battery level, etc. And the action could include numbers representing how fast to spin a motor, which direction to go, which ability to activate in a video game, etc. Now remember, where exactly you draw the boundary between agent and environment is actually more nuanced than you might think. And it depends entirely on your realm of control and what specific task you're trying to achieve. Only what you can directly control, what you can take for granted, is the agent. For example, imagine I'm learning how to drive a car, but I'm starting from zero. I don't even know how to move my limbs yet. We need to write a program. Let's call it Program A, and put it in my brain in order to learn how to move my limbs. Here, what we can directly control are the neuron signals that my brain sends down my spinal cord into my muscles. What we cannot directly control, but are trying to influence indirectly, are the movements of my limbs. So we can say the agent is my brain, the environment is my limbs, the actions are my neuron signals, and the state includes the positions, joint angles, and movements of my limbs as observed through visual feedback and proprioception. Now, pretend we've fine-tuned this program enough, so now I'm pretty confident with limb movement. In my forearm, for example, I can open and close my grip, do some wrist flexion and extension, and occasionally, if I'm feeling extra adventurous, maybe even dabble in some ulnar and radial deviation. Now we have to write program B to control how I'll interact with the car. The agent is me as a living creature, the environment is the car, the actions are my limb movements, and the state consists of the elements of the car, which I can observe visually, such as looking at the speedometer, or through tactile feedback, like gripping the steering wheel or stepping on the brakes. Now that I know how to operate the car, I have to learn to drive using Program C, which, let's say, can now directly control how the car moves forwards and backwards and how it turns. Now the agent is the whole car, the environment is the road, the actions are just how the car moves, and the state includes other cars and their positions, how many lanes there are, what the speed limit is, etc., which I observe visually. So in this agent environment model, the boundary between agents and environment can be quite arbitrary, and the time scale for these actions and state observations can also be quite arbitrary. Like for example, if I close my fist, is that one action? Or is it 5 actions, one for each finger? The good thing about this arbitrariness is because you can frame a problem in so many different ways, you can choose to frame it in a way that gives the problem structure and makes it easier to solve. So let's go over the way that reinforcement learning frames a task in order to solve it, which is called the Markov decision process. So first of all, there's also this added signal known as a reward, which is just a single number that comes after each action that represents whether that action had a good or bad outcome. The more positive the reward, the better, and the more negative the reward, the worse. Now, it's up to you to interpret whether the reward comes from the agents or the environment. If it's a human learning something, we can generally decide for ourselves whether we did good or bad at that task. But if you're training a dog, then the reward of food seems to be provided externally. Conventionally, the reward is considered to be a signal from the environment to the agent, so let's stick with that. So now let's write out what a Markov decision process is, also known as an MDP. It's a discrete, repeating, one after the other sequence of state, action, reward, state, action, reward, state, action, reward, and so on. This can either go on forever, or it can terminate, like if you're playing a level in a video game and you die on that level, in which case it's called an episode, and the episode terminates. Just a small note on the notation. Here I've chosen to have the time step of the reward take on the time step of the state and action before it. So it would go S0, A0, R0, S1, A1, R1, etc. This is because I thought it makes more sense this way. However, I found out that in other sources about reinforcement learning, usually they have it so the rewards time step is the same as the state and action after it. So it goes S0, A0, R1, S1, A1, R2, etc. This is not a huge deal, but as a result, in some of the later mathematical formulas, you might see that it's a bit different compared to those formulas in other sources, where the time step of the reward is off by 1. Other sources also often choose to use uppercase letters, like capital R, but here I've chosen to use lowercase r. Once again, not a big deal. Let's get on with the video. Ideally, this sequence must follow a rule called the Markov property, which means that each state is only dependent on its immediately previous state, and not any other states. For example, if you're making a robot to catch a ball, and you've designed it so that the state information it receives only includes its position, then it's unclear what the next state will be because it's unclear in which direction and how fast the ball is moving. You would have to look at multiple consecutive states to deduce that information. If instead you also included the velocity in the state information, then it would follow the Markov property, and each state is only determined by the immediately previous one. Of course, the robot isn't necessarily going to know how gravity works, or how one state transitions to the next, but at least there's sufficient information for it to learn that. Now, MDPs, are they perfect? Do they apply to every single situation? Probably not. First of all, lots of RL methods rely on this Markov property so that they can just go off of the most recent state to decide on the next action and keep it simple. But obviously, not all situations are going to satisfy this Markov property. And if we have certain states that depend on more previous states, then the tools that we develop using this framework aren't going to work as well. Also, with a simple sequence like this, it's hard to deal with varying timescales. If you want to work on the scale of individual muscle movements in one moment, and then in the next moment zoom out to, let's say, which city to drive to, then you'd probably need a more complex framework than that. Another thing is, there's only one single number as a reward signal. If you're doing tasks that are more nuanced and can be evaluated in multiple aspects, then maybe having only a single number as a feedback for each action can be a bit limiting. But this is pretty much the best that we've been able to come up with so far. And basically all of reinforcement learning is built on the foundation of MDPs. Maybe in the future, someone could figure out a way that works better. Maybe that could be you, the viewer. But anyways, let's talk about some of the maths in an MDP. Within an MDP, the ultimate goal of the agent is to figure out how to, for any given time step, use an input state to decide on an output action in a way that maximizes the total subsequent reward over time. So let's cover these two mathematical constructs: the strategy that takes a state and decides on an action, and the cumulative reward over time. The strategy, we call that the policy function, represented by the symbol pi. You can intuitively think of it as a mathematical function that takes a state as an input and gives an action as an output. But technically, the notation for this policy function is usually written a bit differently to allow it to have some randomness. As in, given the same state, the policy can produce a range of different actions, each with their own probability. The randomness is important for exploring different strategies. So RL people usually write the policy function as giving the probability of picking a certain action given, this vertical bars are conditional, given that you're in a certain state. Now, the next thing, the total cumulative reward, is called the return, represented by capital G with a subscript t. The subscript t represents which time step it's for. So for example, if we're talking about the sum of rewards starting from R1, then that would be G1. This is just all the rewards added up starting from time step t and progressively multiplied by this discount factor gamma in increasing powers. Now, gamma is just a number between 0 and 1, and this can be lowered to make rewards in the future less significant, perhaps because the future is inherently harder to predict. So maybe you'd want that to factor less into your decision making. Or gamma can just be set to 1, in which case this would be an undiscounted sum. But then it would only work for terminating episodes, or else it'll just add up into infinity. Of course, it's better to try to maximize the total reward over time instead of just the immediate reward for a single time step, because what gets you more reward immediately might make you get less reward later on, kind of like delayed gratification. So remember how the goal is to, for any given time step, use an input state to determine an output action in order to maximize the total subsequent reward over time? Using this mathematical terminology now, we can instead say that the goal is to find the policy which maximizes return. Find the policy which maximizes return. Alright, let's try applying this to a practical example. Usually, when you're teaching RL, you start with some sort of task involving a grid, and we're going to do that too. The reason is that even though no real-life problem will ever be this simple, in a grid, each state corresponds to a single square, so it's really easy to visualize and demonstrate some key concepts, like the exploration-exploitation trade-off, temporal difference, the credit assignment problem, world models, and sample efficiency. Using our simple grid demo, we're going to go through what each of these terms mean, how they relate to each other, and why they're important for reinforcement learning. We have a maze, well, a really simple one with just one wall, but let's still call it a maze, where the agent starts on a certain cell and must get to the target cell by moving up, down, left, or right. And it cannot move through walls. The maximum episode length is 20, so the episode terminates when it either reaches the target or when it's been going for 20 steps already and still hasn't reached the target. Let's start thinking about how we can apply the theory we've developed so far and frame this task as a Markov decision process. So first, we'll need to define a state, action, and reward. So each state will be two numbers representing the xy coordinates that the agent is on. Each action will be a single number between 0 and 3 representing either up, down, left, or right. The reward after each action will be 0 if the agent enters the target cell, or -1 otherwise, which makes it so that the goal is to arrive at the target as fast as possible. So here we can talk about our first concept, which is world models. As humans, we can obviously see the whole maze at a glance and immediately figure out how to solve it. Because we understand that the states represent coordinates, the actions represent directions, and how the reward works, we know that if you're in the state of 0, 0, and you pick the action of 3, representing right, that you'll move into 1, 0, and get a reward of -1. We also know that in 1, 1, if you pick 3 and try to move right, then you'll stay there because there's a wall in front of it. If the agent also understands this, then we say that it has a world model, or a model of the environment. Mathematically, this just means having access to this function, sometimes denoted as P, which tells you, given that you picked a certain action in a certain state, what reward and next state will it lead to? Or more precisely, to account for some randomness in the environment, what's the probability of any next state and reward given a combination of being in a certain state and picking a certain action? A function like this is an example of a world model. It turns out that whether an RL agent has access to a world model, whether it understands how the world works, makes a massive difference to how well it can learn to do tasks, which obviously makes sense. This is also why a lot of the current research in RL is concerned with how to develop better world models, or make agents learn better world models on their own. for complex tasks. With our maze task though, we're going to start by focusing on model-free methods, which assume that the agent does not have access to a world model. In other words, the agent cannot see the whole maze at a glance like us humans. It doesn't know what these state and action numbers represent or how they relate to each other, and it doesn't understand how the rewards work. So it doesn't know that if you're in 0, 0 and you pick 3, you'll end up in 1, 0, for example. The states, actions, and rewards are just meaningless random numbers, and the agent has to somehow learn to pick actions in a way that maximizes the rewards it gets. So without access to any information, all the agents can do at the start is just randomly pick actions, meaning that instead of using a policy where there's actually meaningful probabilities for the different actions, it's effectively using a policy that looks like this. For all these meaningless input numbers, all the meaningless output numbers have the same probability, and we're meant to somehow improve this policy over time. So by picking random actions, of course, most of the time it gets nowhere and receives a total reward of -20, since the episodes are capped at 20 steps. But the important thing is that it's writing down all of its experiences in order to learn from. This process of trying actions is called sampling, and all these sequences of state action reward are known as trajectories. The agent is collecting sample trajectories. Eventually, due to sheer luck, there will be a few trajectories where it actually does reach the target, and these are the important ones. Let's see how the learning happens. So first, we're going to now use this other mathematical concepts that we've developed and calculate the returns for each time step in our successful trajectory, using a gamma of, let's say, 0.8. The way we can do this, because of the way that later rewards are progressively multiplied by gamma, is we can start at the end and work backwards. The return of the last time step will just be 0. And to get to the previous one, you multiply that by gamma, and then add on the previous reward. Then to get to the previous one, you multiply that whole sum by gamma, and add on the previous reward again. Then you repeat. In the end, you'll find that even though this is a successful trajectory, all the returns are negative, because all the rewards are negative, obviously, except for when the agent reaches the target. But in the unsuccessful trajectories, all the calculated returns are going to be even more negative, because the agent never reaches the target, so it keeps collecting the -1 rewards for the full 20 time steps. So now that we have all our sample trajectories and we've calculated the returns for each time step, we have to somehow use these experiences to achieve a better policy. There are different ways that you can go about this. You can directly work with these probabilities, for example. Push the probability up for actions that had good returns, and push the probability down for actions that had bad returns. That would be called a policy gradient method. Gradient meaning rate of change, and we have to calculate how much to change the policy based on which actions are good and which actions are bad. But doing that requires us to know what's considered good and what's considered bad. Consider this example where we have 3 actions, initially all set to the same probability. Let's say we collect a lot of sample trajectories, and on average, action 1 gives a return of -5, action 2 gives a return of 0, and the third action gives a return of 5. Then it's pretty straightforward. You push the probability for action 1 down, keep action 2 roughly the same, and then push action 3 up. But what if instead action 1 gave 5, action 2 gave 10, and action 3 gave 15? Or what if it's 95, 100, and 105? Or if it's like our maze example, where everything's negative. See, the issue here is not that all 3 numbers are positive or negative, and you can't increase or decrease all probabilities and still have them add up to 1. When you're actually using policy gradient methods, the effect on the probabilities is more like a tug of war, especially with neural networks, which have this thing called a softmax function that makes sure everything adds up to 1. The real issue is that proportionally, the effects are now different. 10 to 15 is a 50% increase, while 100 to 105 is only a 5% increase. What we want is for all cases to have the same effect, because an increase of 5 is an increase of 5 no matter what. Especially since within the same environment, maybe some states are just better on average, and some states are just worse on average, no matter what action you take. So what we need is these things called value functions as our baselines, which keep track of the average return you should expect to get when you're following a certain policy, and help evaluate how good or bad states and actions are. V is the state value function, representing how much return you should expect to get when you're in a certain state and follow a certain policy. Q is the action value function, representing how much return you should expect if you're in a certain state, pick a certain action, and then follow the given policy. Notice that these functions necessarily have a policy function attached to them, because if it's a different policy function, the actions that are picked will be different. So naturally, you would expect to get different returns. These are just random example numbers that I made up, but the key is that it's different for different policies. In fact, the state value function is basically just all the action values within that state, averaged according to the probabilities given by the policy. If you just want to not care about which specific policy it's talking about, and refer to what's the best case scenario if you somehow picked the best action every time, then that would be V star and Q star, the optimal value functions. We've written these value functions not as probabilities without any randomness, unlike the policy and world model up here, because RL is still developing, and up till now, people have not yet considered randomness and variance for the value functions as much. There are fields of research though, like Bayesian RL and distributional RL, which do consider variance in value functions, which you can think of as like risk to reward ratio, as in how good a state or action is, but also how uncertain that goodness is. There are so many unanswered questions in RL. But anyways, that's our value functions. Once we have our value functions, then we can improve our policy. And now we have a few different options as to how we do this. First, we could just use the policy gradient method we talked about before without using a value function baseline. There's issues with that, as we've said, with the different averages, it doesn't work that well. And then we could also use the policy gradient method with a baseline, such as our state value function, to compare with all the different returns in the same state. Now this works better as all these cases with different averages can be made to all have the same effect. But it turns out there's also another method, which is instead to just look at the action value function and pick the action with the highest estimate every time. In other words, the policy doesn't keep track of different probabilities anymore. 100% of the probability just goes to the action with the highest estimate. Well, not quite, because some randomness is needed, or else there will be issues, as we'll see. But now there's this cyclic dependency, because usually the action value function is based on the policy function. But now the policy function is also based on the action value function. So with this cyclic nature, as long as you keep improving the accuracy of the action value function, as we'll see later, the policy will improve alongside it. Out of the three methods, you can essentially think of the first method as being more dependent on the policy function, the last method as being more dependent on a value function, and the middle method as being a balance between the two, taking the best of both worlds between the policy and the value function. All of them have their advantages and disadvantages, but this balanced method does tend to be the most powerful out of the three. What I want to do though is focus exclusively on the problem of evaluation for now, the problem of how to develop good value functions. Having good evaluation is very important to having good improvement. So let's first focus on this last method, this action value method. Even though it has its disadvantages, which we'll get to later, it allows us to not worry about the policy function for now and just focus on some key concepts for good evaluation. So of course, the whole point of evaluation is we don't just magically have access to such an action value Q function, and must develop one and make it more accurate over time. The simplest way we can do this is just to take the trajectories we collected and then average out the return values for each combination of state and action. We can imagine that for every possible state action input, the output of this Q function will initially be set to 0, as shown in this table. Of course, the agent has no knowledge that the table is supposed to be a 5x3 grid, like the maze, but I set it up like this just to show the values that will actually end up changing. So with every new return value, remember we're working backwards, so let's say this state of 4, 1 plus this action of 1, which would correspond to this right here, we would move the value for that specific state action pair towards this result by a small amount, let's say 10%. Now in this case, since they're both 0, it wouldn't matter, but it would be with a calculation like this. 0 plus 0 minus 0 times 10%, which is 0.1. This is an example of how we could gradually adjust these values. Of course, it'll be 0, so nothing will change, but let's say the previous one with 3, 1, and 3, the result is minus 1, so we would say 0 plus minus 1 minus 0 times 0.1. And then we would update our table with this new result. Now for the sake of time, I'm not going to do all of the values, but just to demonstrate, here we have two instances of the same action value pair of 1, 0, 3. So for example, first of all, it would be minus 4.57, so that our result is now minus 0.457. And then when we get to the other one, now we have minus 0.457, because it's what value was originally there, plus the new result of minus 4.73 minus the existing value, and then times 0.1. So the new value is now more negative and adjusted towards whatever results we are using. So this constant shifting of our values towards these new results by a small amount is how everything gets averaged over time. And over many iterations, the good states and actions will end up having a good value in this function, and the bad states and actions will have bad values. Ideally, eventually, it'll be able to approach our actual environment. Obviously, the states that are closer to our target should have better values, and the states that are farther away should have worse. So let's run the simulation for lots and lots of episodes. In the beginning, the trajectories don't really get anywhere. But what you see is, over time, the Q function that we are developing, which evaluates the policy, becomes more accurate. And because it becomes more accurate, the policy, which picks the best action based on the Q function, also improves. But because the policy improved, the Q function is now evaluating a slightly different policy, and has to become more accurate for the new policy yet again. And then after that, the policy improves again. Because of this cyclic dependence between the policy and the Q function, the improvement happens in a cycle, known as generalized policy iteration. Eventually, the goal is for the Q function to approach the Q star function, where it accounts for the best case scenario out of all the different ways of picking actions. Then, naturally, the policy based on this optimal Q star function will also be the optimal policy. Here in the corner, we have some results to track how the agent is improving. But oftentimes in RL, you track improvement using total undiscounted reward, as opposed to discounted return, which is what's used for the training. That's not too important, but what is more important is this variable over here, called epsilon. And what it does is help maintain a balance between exploration and exploitation. This is one of the downsides of this action value method. The reason the agent was able to develop the value function in the first place was by following a random policy and gaining all these diverse experiences. That's known as exploration. But once it actually wants to use the value function to perform better and get more rewards, known as exploitation, then if it just picks the action with the highest value every time, then there's no randomness anymore. The probability distribution ends up being one action having 100% probability and all the other actions having 0. When you're improving in RL, what you need is a balance between exploration and exploitation, so that you can both try out different things to improve and also take advantage of that improvement to perform well. Now, with policy gradients methods, that is not a concern. Since you're adjusting a whole bunch of different probabilities, it'll naturally have some randomness, even if certain actions tend to be more optimal. But with this action value method, where you're just picking the best one, we have to use this hack called epsilon greedy to kind of artificially introduce some randomness back in. Basically, epsilon represents the proportion of the time where the agent picks a random action, and it's supposed to gradually decrease. For example, you might have epsilon start off as 0.9, meaning you pick randomly 90% of the time and pick optimally 10% of the time. This is because what the agent thinks is optimal is not very accurate at the start. But then, as time goes on and the action value estimates become more accurate, epsilon gradually decreases to 0.1, which is 10% random, 90% optimal. This method that we just covered is known as a Monte Carlo method, which, according to Wikipedia, is just a computational algorithm that relies on repeated random sampling to obtain numerical results. We used random sample trajectories to figure out what the values of the Q function should be. Now let's look at what the limitations of this method are and what we can improve upon it. The main issue with Monte Carlo methods like this is that it works on an episode-to-episode basis. When we collect our trajectories, we've got good episodes and bad episodes. In the good episodes, all the actions will be evaluated better, and in the bad episodes, all the actions will be evaluated worse. The first problem this results in is that you have to wait for the episode to end before you can even calculate any returns and adjust your evaluations for the actions. If the episodes are really long, then that's going to be really slow. And if it's a continuing task, meaning it just keeps on going and doesn't terminate, then this method won't even work. The second problem is that within the same episode, you don't know which actions were good and which actions were bad. Take our successful trajectory, for example. If we draw out what the path actually looks like on the maze, then it's clear that some actions were the right decision and some were not. Using Monte Carlo methods, we can only rely on the large number of samples to average out and hopefully correct for this suboptimal action. We have now run into the credit assignment problem. The problem of figuring out what the impact of an individual action was within a long sequence of many actions. So how can we try to solve the credit assignment problem if the agent is just working with these trajectories and cannot see the whole maze at a glance like us humans? The answer is a concept known as temporal difference, which breaks down evaluation to an action-by-action basis rather than an episode-by-episode basis. Here, let's imagine that in these two graphs, the magnets represent time steps in a trajectory, and we're using them to help construct a Q function, which estimates how much return you'll get if you're in a state S, take action A, and then follow policy pi. In Monte Carlo methods, you're directly calculating the returns in an absolute sense by adding up all these subsequent rewards like we've done on paper with these trajectories in order to contribute to this estimate. That's why you have to wait until the episode ends. However, in a temporal difference method, even though we're still trying to construct an estimate of the returns, we don't directly calculate the returns by adding up all the subsequent rewards. Instead, you come up with an estimate for each state action pair relative to the estimate for the state action pair in the time step after it, using just one reward as the difference, not all the subsequent rewards. The terminal states at the end of episodes, which don't have a reward and next state afterwards, stay at 0, acting as an anchor around which the other values develop. If it's a task that continues forever and there is no terminal state, then there is no absolute reference point as an anchor, and all the values might drift up or down. But since you just need to know their values relative to each other to pick the best one, that's not necessarily an issue anyways. The actual math that describes this relativity is like this. If we write out a return as a discounted sum of rewards, then we can see that we can take out the first reward and the rest of it will just be the next return in the trajectory multiplied by gamma. Of course, returns refer to within a specific trajectory. So for our more general, averaged out estimate for states and actions, we can replace the GT with Q and move our estimate towards this result by 10%, for example, like we did before. Now here, for the next state and action, we've just used the state and action that happened to occur in the sample trajectory. But since the environment has some randomness, this might not be the only subsequent state that's possible. And since there's a range of different actions you can take, this is also not the only subsequent action that's possible. We can't do much about the state because we're talking about a model-free method right now, so we don't have access to a world model and don't know the next state transitions. But with the action, as you may imagine, there's a couple other ways that we can decide what action to put in here so that we can make this calculation. For example, you can account for all the possible actions averaged out according to the policy probabilities. Here, it's a weighted sum across all the actions where you multiply by the probability. Or you could take the best action with the highest estimate rather than the one that you ended up taking. Here, you're taking the maximum out of all the actions. This algorithm is called SARSA. This one is called expected SARSA, and this one is called Q-learning. In other words, for any given state and action, Monte Carlo is saying, what is my return? SARSA is saying, how much better or worse is my return relative to the new state and the action that I ended up taking. Expected SARSA is saying, how much better or worse is my return relative to the new state with all of its actions averaged out according to policy probabilities. Q-learning is saying, how much better or worse is my return relative to the new state with its best case scenario highest estimated action. Of course, alongside these different ways of learning the action value Q function, you can also learn the state value V function, like so, where it's a bit simpler because it only takes states as opposed to states and actions. Right now, we're focusing on the Q function, so this V function is not that important, but do remember it because it'll come up later in the video. Furthermore, I've written out the math in simplified form with an arrow, and just described it as moving one value towards another value. But mathematically, it's like this, where you assign to your estimate what it originally was, plus the difference between the target and the initial value, multiplied by some sort of learning rate alpha, which we've used 0.14 up until now. Anyways, that's just the actual math of it, if you're curious. Now, notice how a Q function is usually supposed to have a pi attached to it because it's evaluating for that given policy. But here, for these different ways of constructing estimates, I haven't put a pi on them, and that's because they are estimating different things. For SARSA and expected SARSA, notice how we're constructing the estimates based on what action the policy ended up taking or what action it's expected to take based on the policy's probabilities. In these two cases, since the estimates are based on the policy pi, then it's estimating Q pi. And then remember, through this continuous cycle of estimating Q pi, and then using it to improve pi, and then estimating the new Q pi again for the improved pi, called generalized policy iteration. Eventually, Q pi will become the optimal Q function, Q star, and pi will become the optimal policy. But for Q-learning, if we're constructing the estimate based on the best action to take in the next state, then it's no longer dependent on any policy, like the other two. That means instead of estimating Q pi, which will hopefully eventually become Q star, it instead directly estimates Q star. So there is a terminology to describe this difference. The first two are called on-policy methods, where the behavior policy, the policy used to gather experiences, is the same as the target policy, the policy that is being evaluated or improved. These two are evaluating pi, which is the policy that's used to gather the experiences and trajectories in the first place. The last one is called an off-policy method, where the behavior policy is not the same as the target policy. It still uses the policy pi to gather experiences, but it's not trying to evaluate the policy pi. It's instead trying to evaluate the optimal policy directly. So Monte Carlo, SARSA, expected SARSA, and Q-learning, all these methods differ in their sample efficiency. What that means is the number of samples, either the number of episodes or the number of time steps that it takes to get good at a task. If, for the same task, one method requires 100 episodes to get good at it, and another method requires only 50 episodes, then the 50 episode method is more sample efficient, and that's what we want. Usually, Monte Carlo is the least sample efficient, because the other three have taken advantage of temporal difference, and it has not. Then it's usually followed by SARSA, which is more sample efficient, and then expected SARSA, which is even more sample efficient, and then finally Q-learning, which is the most sample efficient, because it has taken advantage of both temporal difference and off-policy learning. Now, off-policy has its advantages and disadvantages, but this sample efficiency is sometimes one of the advantages of off-policy learning. Now, we've said that Q-learning tries to estimate the optimal Q-star function through updating like this. There's an equation that describes what this optimal Q-star function will actually end up being. Remember how the environment is random, and after you take a certain action, you won't always end up getting the exact same reward or the exact same next state. And this is of course described by the world model function that gives the probability of the different rewards and next states which we don't have access to. Well, if you do Q-learning with enough sample trajectories, it will average out and you will end up approximating this optimal Q-star function, which is supposed to be the expected value of this relationship we have been trying to capture. The expected value is just a weighted average, similar to an expected SARSA, but this time according to the probabilities in the environment, meaning that even though we don't have access to this world model, the samples we collect will still average out according to it. Furthermore, aside from this expected value, the expression inside it expresses a property called Bellman's principle of optimality, which, if you look on Wikipedia, is a quote from some guy called Richard Bellman, who was figuring out some of this math back in the 1950s. It says, an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. What this means is if there's a series of decisions which is optimal as a whole, then if you look at all the decisions except for the first one, those have to be optimal too. Which kind of makes sense, right? If you want to get full marks in a test, and the test is split into 3 sections, then naturally, that means you must get full marks in each individual section. It sounds pretty obvious, but back then, this was groundbreaking stuff. So that's kind of the theory behind putting a max around this subsequent bit in order to find the optimal Q function. And this is called a Bellman optimality equation. There's a Bellman optimality equation for the other value function v as well, but we're focusing on Q for now. I don't think it's too important to know the historical context and terminology for this bit of math, but everyone who teaches RL mentions it, so I thought I'd include it as well. To quickly demonstrate how Q-learning works in practice, here's the table again, with some random numbers filled in. Let's say you're in this state, picked this action, and then ended up in this state with a reward of -1. Then you'd simply look at the new state, find the maximum value out of all the actions there, which is this one, multiply it by gamma, and then add on the reward. Once you have that result, you simply go back to the original state and action, and then move that value towards it by a learning rate of 10%, for example. This way, you only need the reward for one time step, and you don't have to add up all the rewards in a trajectory. So let's run the simulation again with Monte Carlo and Q-learning side by side, and see if it has any improvement. Here, I've made it so they both use the same epsilon. they both use the same gamma of 0.8, and they both use the same learn rate of 0.1, or 10%. For this small maze, there is a bit of an improvement, but the difference is not that big. If we switch to a bigger maze though, then immediately you can see that Q-learning is doing way better, and Monte Carlo is never able to reach the target square even once. The benefits of a more efficient algorithm really start to show in more complex environments. Now, you might be thinking that this is only because Monte Carlo was never able to reach the target even once, and it just got unlucky. So to see what would happen if Monte Carlo did have some successful experiences, I did another run, where for the first 50 episodes, it was artificially helped to move to the target as efficiently as possible. But even after that, Monte Carlo failed to reach the target again in the rest of the run. The point is, Q-learning is better. So now that we've gotten up to Q-learning, which is more sample efficient than the other ones, we have finally gotten good enough at the fundamentals that we can slap on a neural network and move past this grid example. The main benefit of neural networks is that we can go from discrete states and actions to continuous states and actions. In other words, instead of only having whole number positions and a limited number of actions in this grid, neural networks can allow for an infinite, continuous range of states and actions. As you can imagine, this is necessary for basically any real-world physical task, where you're dealing with things like angles, velocities, positions, and directions. It's impossible to use a table for continuous states and actions, because you can't have an infinitely big table. The first algorithm we'll look at is called Deep Q Network, or DQN, which takes us halfway there, as in it can allow for continuous states, but not continuous actions. So we'll try and solve a task called Lunar Lander, where you're supposed to activate the engines on this 2D spaceship and try to land it in the middle. The task is designed so that there's 3 engines, which are either on or off, and you can only turn on one at a time, which means there's 4 discrete actions, one for having no engines on and one for each engine. The reason Deep Q networks only allow for a limited discrete number of actions is because it's a value-based method. Remember how there's methods that are more reliant on the policy function, methods that are more reliant on value functions, and methods that are a balance between the two? Up till now, we've been focusing on the last category, where Monte Carlo, SARSA, expected SARSA, and Q-learning are all value-based methods. They all evaluate actions, so obviously you can't just evaluate an infinite number of actions in order to pick the best one. For continuous actions, we'd have to go back to policy gradient methods, which we'll look at later. Anyways, with Deep Q networks, you basically take Q-learning, but swap out the table for a neural network. The table takes input states and actions and outputs an evaluation, and you can go and adjust its outputs over time. Well, a neural network can also take input states and actions and output and evaluations, and then you'd go and adjust its outputs using backpropagation and gradient descent. Well, with a slight adjustment, you take an input state and output evaluations for all the actions simultaneously, because that's more efficient. The neural network is a function approximator, because while with the table, you can keep track of a whole bunch of exact values which don't affect each other, with a neural network, you have a limited number of parameters which affect how all the outputs are calculated. So here is Lunar Lander, with a neural network instead of a table to approximate its Q function. The neural network has layers of 64 nodes each in the middle, so I wasn't able to show all of them, but it's essentially updating according to Q-learning. So it's trying to estimate the optimal Q star function in a way that is off policy, making it more sample efficient. Compared to the grid, this environment uses much smaller time steps and much more time steps. So we are using a gamma discount factor of 0.999 and a learn rate of 0.0001. As you can see, we have our familiar epsilon here, which dictates the probability that it'll take random actions as opposed to the most optimal one. This environment comes from a Python library called OpenAI-Gym, and the state consists of 8 variables: the x and y coordinates of the spaceship, the x and y velocities of the spaceship, the angle, the angular velocity, which is how fast it's spinning, and 2 yes or no values saying whether its 2 legs are in contact with the ground. The rewards at every time step will be higher if the spaceship is closer to the landing pad, moving more slowly, and in a more horizontal position. Whenever the engines fire, it results in a small penalty in the reward to try to get the spaceship to use less fuel, and there's a bigger reward when the legs are in contact with the ground. Finally, there's a massive penalty if it crashes, and a massive reward if it lands safely. Of course, at the start, the untrained spaceship will keep crashing, but over time it does improve. Now, there's actually many variants of DQ networks, also known as DQNs. There's double DQN, dueling DQN, rainbow DQN, etc. These algorithms all differ in the little tricks that they use, but fundamentally, they're all basically taking Q-learning and replacing the table with neural networks. In fact, even this normal DQN, which came out in 2013 in a paper called Playing Atari with Deep Reinforcement Learning, uses a couple of these tricks, such as a target network and a replay buffer. But that's outside the scope of this video. We won't go into all of those tricks. After around 100 episodes, the spaceship has gotten pretty good and pretty consistent as well. It doesn't crash anymore, it stays upright, and whenever it veers off to the side, because there's a random force that's applied to it at the start of every episode to make it more challenging, it's able to slowly readjust and move back into the middle before landing. So let's try and visualize what the network has learned. Here's some examples of outputs from a network trained on Lunar Lander. I've laid it out so that this rectangular area corresponds to the x and y coordinates of the spaceship, which is the first 2 numbers in the state. And the other numbers in the states can be altered down here using sliders. As you can see, it's been trained to the point where you can understand the outputs reasonably well. So when the spaceship is not moving, completely horizontal and not rotating, then it'll not fire any engine if it's right above the target. When it's off to the left, it'll fire its left engine to move back towards the right. When it's off to the right, it'll fire its right engine to move back towards the left. And if it's too far down, it'll fire its down engine to come back up. Other than that, most things make sense, but not everything. If the x velocity is positive, so it's moving to the right, it's more likely to fire its right engine to move back left. But if it's moving to the left, for some reason the left engine is not fired more frequently. If it's got a negative y velocity, meaning it's moving downwards, it's more likely to fire its down engine to slow down. But for some reason, if it's moving upwards, it'll start firing its right engine. If the angle is positive, meaning counterclockwise, it'll fire the left engine more, and if it's angled clockwise, it'll fire the right engine more. The same thing can be seen for angular velocity, which is how fast it's rotating. For comparison, I've also visualized a random untrained network, and it's much harder to see a pattern or explanation in how its inputs relate to its outputs. Now let's talk about policy gradients. If you'll remember from before, this is where we push up the probabilities for actions that did well and push down the probabilities for actions that did poorly. Here, instead of just focusing on evaluation with a value function and having the improvements of the policy be just based on that, we are now separately keeping track of a distribution of probabilities and altering it at will. Furthermore, it turns out that not only can you have a discrete probability distribution, you can also alter policy gradients to work with a continuous probability distribution, defined by a mean and standard deviation, for example, which we'll look at later. This is, of course, important for many tasks where there's a physical aspect, where it's not feasible to classify actions into discrete options. So let's start off by talking about a fundamental difference between learning a better value function for evaluation versus learning a better policy function for improvement. If you'll notice, whenever we have learned a value function up until now, no matter if it's with a table or with a neural network, no matter if it's Monte Carlo or SARSA or expected SARSA or Q-learning, there's always some sort of target that we calculate and then try to get the function to move closer to. And this perfectly fits how a neural network traditionally functions, where you're trying to use gradient descent to minimize a loss function in order to get closer to the targets, or ground truth, that you give to the network. However, in order to improve the policy function with all the probabilities that it keeps track of, what's the target? If we're just adjusting probabilities up and down depending on whether the action did well, then that's more akin to trying out different things and seeing what works. There is no such clear-cut target. Without a ground truth target, we no longer have a loss function to minimize. Without something to minimize, we are instead going to look for something to maximize. What quantity should we maximize so that our policy performs as best as possible? Such a thing is described as an objective function j, which is written in a way that says it takes in the whole policy with all its network parameters, theta, the whole policy, not just a specific state or action, and outputs some sort of evaluation of how well it's doing. So it's kind of like another type of evaluation, but it's different from the value functions such as Q, in that Q, for example, takes a lot of effort to estimate and calculate, and it actually serves the useful function of helping us differentiate between which states and actions are good and which states and actions are bad. J, on the other hand, just evaluates how well the policy is doing as a whole. So we could even say that our graph that tracks total rewards over time is an example of a J function. Calculating the value of J is not that hard and not that meaningful. I mean, we kind of just did with this reward graph, and it doesn't really tell us anything about how to get better. So the point of J is not really to calculate its value, unlike the value functions of Q or V. The point is that when you set it as the thing to maximize for this neural network through gradient ascent, you can end up deriving some pretty useful math that helps improve the policy function. So here's where we have to figure out how to actually define J in order to derive that math. J is often defined as different things in different sources on the internet. This one frames it as what's the expected total reward that you'll get in every trajectory generated by the policy. This one is what's the state value V of an initial state in an episode with a start and end. This one is the average state value V across all states. And this one is the average reward per time step. The point is, it doesn't really matter. They're basically all slightly different ways of saying the same thing, which is how much reward are you going to get on average. The definition of J isn't that important. What is important is that with all these different definitions, if you differentiate it with respect to the parameters theta, with a whole bunch of complicated math involving something called the policy gradient theorem, you end up with something that is generally in the form of this. Now that looks really complicated, so let's break down this equation right here. First of all, this thing right here is the gradient of J with respect to theta, which just means how to change the parameters theta in order to increase the performance as measured by J. And then this thing right here is you take pi of A given S, which is how likely you are to take a certain action, and then you log it, and then you take the gradient of that with respect to parameters theta. That sounds complicated, but basically it's saying how to increase the probability of an action A. This thing right here is some sort of quantity. There's multiple definitions for this quantity, which we'll get to later on. But it's some sort of quantity saying how good is that action A. And then finally, there's this expected value and sum across all the time steps, which is basically to say you're averaging out across all these states and actions. So basically, it's saying in order to increase performance, increase the probability of all actions according to how good each action is. Even though the math looks very complicated, it's basically doing what we said at the start. Push up the probabilities for actions that did good, and push down the probabilities for actions that did poorly. So let's first look at this quantity that says how good each action is. As we've said before, we could just use GT, which is the total return that occurred after that action. But of course, this suffers from the problem that different states might have higher or lower rewards on average, so it's inconsistent and has what we call high variance. We want to figure out ways to reduce this variance. Of course then, we can do what we proposed, which is to use the value function v as a baseline and make it fair for all the different states. But then this GT still suffers from the problem that you have to wait for a whole episode to end, and you can't use temporal difference. So you could also rewrite these two, but replace it with the action value function q. So it could be either q or q minus v, and now we're fully using temporal difference. But then with this q minus v, it's too much effort to have to use two different networks, one for q and one for v. So you can use this equivalence form, which rewrites q as the immediate rewards plus v for the next state multiplied by gamma. So now we only need v. And then we have the most advanced and powerful way, which is a method called generalized advantage estimate, where the math is a bit complicated, so I won't write it out. The point is, there's quite a few different ways of calculating, and they generally aim to go from evaluating how good each action is on its own, which is what we did with the value-based methods like DeepQ learning, to evaluating how good each action is relative to the other actions in the same state, also known as its advantage. And this is with the goal of reducing variance. Notice how the variance was not really an issue with these value-based methods like DeepQ Network, because you're just picking the best action anyways. But now it's important to consider in order to adjust these action probabilities proportionally. So now that we've looked at how to calculate how good each action is, let's look at the other part of the equation, which is how to increase the probability of said action. Here we have two main cases, one where it's a discrete probability distribution and one where it's a continuous one. And we'll say that the continuous one is a normal or Gaussian distribution, so it has a mean and standard deviation. The discrete one is simple. Whichever action it is, you just push the probability for that one up or down. And if you're using a softmax function, the other probabilities will adjust to accommodate it. With the continuous one, the actions will now be a continuous range of numbers. And what you're doing instead is whatever number the action is, you're dragging the mean towards that number proportional to how far away it is. And with the standard deviation, then you can just increase it if the action is far away from the mean and decrease it if the action is close by. Each action is weighted according to how good it is. So now we've covered our two main components of optimizing this objective function. One is adjusting the action probabilities, which is done by the policy function, and the other one is evaluating how good each action is to inform that adjustment. And this is done with at least one value function, sometimes more. If this evaluation process doesn't use this return value that you have to wait till the end of an episode to figure out, and instead fully uses temporal difference, then usually it's called an actor-critic method. Essentially, the actor, which is the policy function, acts, so it picks action and tries to improve. And the critic, which is the evaluation with value functions, critiques the actor in order to help it improve. Now, I don't think it's too important to know the fine details of all this math, as long as you intuitively understand what it's doing, which is push probabilities for good actions up and probabilities for bad actions down, using a range of different methods to evaluate how good or bad each action was in order to improve overall performance. With the mathematical equations specifically, with these typical objective functions, which results in a gradient of this form. Some of the more advanced RL algorithms don't even use this. For example, TRPO and PPO are two algorithms that use what's known as surrogate objective functions, which are like the objective function j, but formulated differently. It looks really complicated, and when the neural network tries to optimize that, it often performs better than when it tries to optimize this stuff. But it still follows the general structure of an actor and a critic. So here is Lunar Lander with a policy gradient method. I've downloaded this trained model from the internet, and it was trained with the algorithm Proximal Policy Optimization, PPO. So a bit different from the classical objective function gradients that we looked at. But essentially, you can see that instead of having one network to calculate evaluations for all actions within a state, we have two networks, one to calculate probabilities for all actions within a state, and one to calculate a single evaluation for the whole state, in order to help with adjusting those probabilities. In this case, the state value function v. Within the probabilities, the red one represents which action it actually ended up picking. So you can see that there is inbuilt randomness here, unlike with value-based methods like deep Q networks, where you pick the best option but artificially add in randomness with epsilon greedy. The next example is called bipedal walker and has continuous actions instead of discrete actions. This model was trained using a method called soft actor critic, SAC, and you can see that not only have we gone from multiple discrete options to one continuous distribution, we also now have multiple continuous distributions for all of the joints of this creature. The actual actions that it ended up taking out of these probability distributions are written here on the right. This time, the advantage is calculated using the average action value function Q for all the actions, instead of the state value function V. Let's talk about one of the most interesting things about reinforcement learning, which is that throughout its development, people have often found links to neuroscience and how the brain works. Here, I'll cover two of the most well-known and well-accepted similarities between reinforcement learning and the brain. The first is with temporal difference and dopamine, and the second is with actor-critic and the dorsolateral and ventral striatum. So let's first look at temporal difference and dopamine, specifically the reward prediction error hypothesis of dopamine. In the 1990s, a scientist named Wolfram Schultz and his colleagues performed a well-known series of experiments on monkeys, where monkeys were trained to press a lever after seeing a light light up as a trigger cue, and as a reward, they would receive some apple juice in their mouth. What happened was, at first, before the monkeys got good at this task, whenever the monkeys got apple juice, their dopamine neurons would get a sharp spike in activity, which makes it seem like dopamine signals reward. However, after the monkeys got good at the task, they learned that the lights lighting up signaled that a drop of apple juice was about to come, and their dopamine no longer spiked in response to the actual juice itself, but rather to the light that predicted it. Afterwards, in a different experiment, there was not one but two levers, and there would be a light lighting up above the correct lever first as an instruction cue, after which there would be the trigger cue telling the monkey to press the lever, after which the monkey would receive the apple juice. Now, as the monkeys got good at this task, the dopamine neurons stopped responding to the trigger cue and started responding to the instruction cue. So this continual shifting forward of the dopamine spike suggests that it signifies not reward, but rather the earliest sign that predicts there will be a reward. So how does this relate to temporal difference? Well, think about our value functions Q and V. Let's say specifically V in this context, which is supposed to predict how much reward an agent will end up getting. The monkeys start off by expecting 0 reward, so their V function starts off at 0. But at whatever point in time the monkey realizes it's going to get a reward, the V function changes to being positive. So conceptually, You can think of this dopamine spike as a surprise, or a shift in expectation, or even a prediction error. Because if the V function was supposed to predict future reward, then you could say that when the new information arrived and it changed, there was a realization that the old prediction was wrong, that there was an error. So that's how you can think of it conceptually. But mathematically, it's a concept called the temporal difference error, or TD error. Remember how when you are learning your value functions, you do so with these temporal difference updates, where you're moving your expectation to some sort of target. Well, in order to do that update, of course, you'd have to first figure out what the difference is between that target and what your expectation is currently. The difference between what you originally expected to get versus what you actually got, plus what you now expect to get with the new information. This is the TD error. Of course, you could write out the TD error for the Q function as well. And in fact, you could write multiple different forms of it since there's different ways of learning the Q function. But we're focusing on the V function here because it's simpler, and the TD error usually refers to the V function. Either way, this TD error is the signal that guides learning. Now remember that through this learning, temporal difference is essentially propagating knowledge of reward back through the time steps, which is what enables this value function to predict and capture information from the future. If there's a consistent cue, like the trigger cue or instruction cue, which you can think of as a state, then the TD error, the surprise of reward, gets propagated back to there, which is why this dopamine shift occurs, until there's no cue before that which can predict it anymore, at which point you can think of it as there not being a consistent earlier state, so this learning cannot happen. What's interesting is the dopamine also showed signs of being a negative shift in expectation. When the monkeys were expecting apple juice, but they accidentally hit the wrong lever, so they didn't get it, their dopamine neurons experienced a sharp drop in activity, signaling a negative temporal difference error. They're now returning from an expectation of positive reward to an expectation of zero reward. So anyways, that's the link between dopamine and temporal difference, the reward prediction error hypothesis of dopamine. Extending upon that is how part of the brain exhibits similar behavior to an actor-critic structure. This is now a more nuanced topic, and I won't be able to refer to one single study that's as obvious as the monkey one. But let's look at a diagram of a human brain. As you may or may not know, different parts of the brain are responsible for different things. You've got areas responsible for sensory input, motor output, visual perception, language and speech, etc. This image shows the outside of the brain. If we look inside the brain, you'll see we have this green bit here called the striatum. And that's responsible for, according to Wikipedia, motor and action planning, decision making, motivation, reinforcement, and reward perception. Sounds familiar to what reinforcement learning is doing, right? Well, it turns out there's been extensive evidence that two subparts of the striatum in particular behave similarly to an actor and a critic. The dorsolateral striatum participates in action selection and execution, like the actor, and the ventral striatum participates in evaluation and prediction in order to guide the actor, like the critic. This 2008 article goes into detail on the topic, and they've provided a neat little diagram here, where on the left side are the components of our typical reinforcement learning framework, and on the right side is how their functions map onto parts of the brain. If you'll see here, in a usual actor-critic RL algorithm, the TD error feeds into both the actor and the critic. From our previous section on dopamine, you might remember that the TD error is a signal that guides learning of a value function, so it makes sense that it feeds into the critic. But you might also remember that in the math of policy gradients, one of the ways of calculating advantage is also the TD error, so it also informs the actor on how to improve. And sure enough, in the human brain, the dopamine signals, which are supposed to behave like the TDR, feed into both the ventral striatum and the dorsolateral striatum. That's just one part of the evidence that supports this correlation, which we are able to understand with the stuff that we just went through. The other evidence involves a lot more neuroscience knowledge, which you might be able to see with all these fancy names of different parts of the brain, so we won't go into that. So the correlation between temporal difference and dopamine and actor critic and the dorsolateral and ventral striatum, those are two of the main links that have been discovered between reinforcement learning and neuroscience. Now I'll talk about some of the key subfields in reinforcement learning that I think are the most important for it to develop in the coming decades. Evidently, we don't have robots in our homes that can fold our t-shirts yet, and some of the main issues still holding back RL are covered in this famous article from 2018, titled "Deep Reinforcement Learning Doesn't Work Yet." Many of its points are still relevant today. One of the main points was that RL can be really unreliable, meaning that you could write some code to train a model and run it 10 times without changing anything other than the automatic random seed that all the networks are initialized by. And then half the time it works and half the time it doesn't. Indeed, when I was trying to train Lunar Lander, with policy gradients specifically, when I ran the code multiple times without changing anything, there were enormous differences between the performance of different runs. This is part of why I ended up just downloading a model from the internet, or else I wouldn't finish this video on time. Reinforcement learning can also be really sample inefficient, meaning it takes an insanely high number of time steps and episodes to train models. In the article, it talks about how Rainbow DQN, which was one of the best RL algorithms for learning Atari games, was able to reach human-level performance after 18 million frames. Now, how long is 18 million frames? Assuming 60 frames per second, that's 83 hours. So on tasks that might take a normal human a few minutes to learn, reinforcement learning takes an almost laughable amount of time. Now, that might be fine for video games where you have infinite simulation anyways, but if you're trying to apply reinforcement learning to situations where you cannot be so sample inefficient, like the physical world, then it's not practical to require 10 million, 50 million, or even 100 million frames of training like some of these research papers show. The article had many more points, so you could go check that out if you're interested. But the main point here is to talk about some key subfields of RL that are still in continuous development and will hopefully help resolve some of these problems. I'll specifically focus on two subfields: model-based reinforcement learning and imitation learning / inverse reinforcement learning. The first one is model-based reinforcement learning. This refers to that world model function that we talked about, the one that we assumed we do not have access to throughout the whole video. It's a very complex and difficult topic that takes way too much time to cover in this video, but essentially, a world model can help you predict the next state and reward if you take a certain action in a certain state, meaning that it encodes some sort of understanding of how the world works, which allows you to imagine and simulate how things will turn out. Model-free reinforcement learning, which we have been covering up until now, I think is not a very practical way of learning. For example, let's say I'm doing a task where if this tennis ball touches the table, I lose points. Without a world model, without any understanding of the environment, it's basically like, I wonder what happens if I let go of the ball here. Oh, I lose points. Well, what about if I let go of the ball here? Okay, I also lose points. Well, what about here? Oh, okay, I also lose points. And then maybe after 300 trials, I'll figure out that if I let go of the ball above this half of the table, I'll lose points. And then I'll need another 300 trials to figure out what happens if it's this half of the table. Now, as a human, if you learn like that without basic understanding of the environment, with stuff like contacts between objects, inertia, and gravity, you look stupid. And if you think about it, that makes it all the more impressive that reinforcement learning is able to do all these tasks without a world model, without any understanding of the environment. But that's also why it takes 10 million, 50 million, 100 million frames. The next time you do any everyday task, take notice that a world model is essential to understanding what's going to happen to a t-shirt when you fold it, which way you're going to fall when you lose your balance, how the water flows in a cup when you fill it up, etc. So, model-based reinforcement learning. In order to obtain a world model, there's two methods. A world model can either be handcrafted and given to the agent, like if we already know the physics in an environment, or if we already know the rules of a board game, or it can be learned by the agent at the same time that it learns a policy or value function. And then once you have the world model, you can also use it in two main ways. You can either just train as usual, but with imagined, simulated experiences from the world model, kind of like that study which found that people were able to improve at shooting free throws by imagining themselves shooting free throws. Or you can use the world model to plan ahead while you're actually doing the task by simulating different possibilities and searching for the best option. A way of doing this is Monte Carlo tree search. Monte Carlo meaning simulated, tree search meaning considering how different possibilities of the future may branch out and searching for the best one. Google DeepMind has some good examples of model-based RL methods, developing over time from AlphaGo to AlphaGo 0 to AlphaZero to Mu0. Over time, they've made the model able to do more and more tasks, expanding from just Go to other board games like chess and shogi, and then to Atari games as well. The first three are given a model and only use the model for planning. The last one, Mu0, learns a model by itself and uses the model for both learning from imagined experiences and planning. Another example is the Dreamer series, with Dreamer and then Dreamer v2 and then Dreamer v3. These ones learn a model by themselves and use the model only for learning from imagined experiences and not for planning. The most recent version, Dreamer v3, was able to obtain diamonds in a modified version of Minecraft, so that is very cool. As you may imagine, world models are very complicated and advanced, so we won't go into it too much here. The second key fields of RL, actually two closely related fields with a similar goal, is imitation learning and inverse reinforcement learning, which aim to learn from a so-called expert's demonstrations. If we think about many day-to-day tasks, such as tying shoelaces, folding a shirt, or even shooting a basketball, almost all of them are usually learned by watching someone else demonstrate. You wouldn't expect a 3-year-old to learn how to tie shoelaces just through trial and error. So if we want robots to one day learn tasks of similar complexity, it would be great if we could somehow teach through demonstration. The earliest attempts to achieve this goal were through something called imitation learning, which is trying to learn a policy, a mapping from states to actions, not from a reward signal, but just from example trajectories from someone who supposedly knows what they're doing. So, for example, if I want to teach an agent to drive a car around a racetrack, I'll just drive it around the racetrack myself a couple times, and then record the states and actions that occurred as training data. Now notice how there's no need to design a reward function here, which is actually a pretty great feature, because designing reward functions can actually be quite difficult to get the agent to do exactly what you want it to do. For example, if I'm not careful and I just give the agent a reward for passing the finish line, it might end up just going back and forth across that finish line to collect a reward, instead of actually going around the racetrack, and that's not what I want it to do. If we think about an even more complex task of just generally driving safely, changing lanes and signaling turns, etc., how do you even define the reward function for that? These are examples of where an expert's demonstration could be greatly useful. Anyways, without the reward function, the simplest way of learning the behavior within imitation learning is to learn a policy just from the generated trajectories, such as with a table or a neural network. And this is called behavioral cloning. However, the issue with that is it works fine when the agent is able to perfectly follow the example trajectory. But if it veers ever so slightly off course, it won't know what to do because the examples didn't cover that, and it'll just keep deviating more and more. To solve that, there's an improvement upon behavioral cloning, which is still within the realm of imitation learning, called dataset aggregation, or DAGR for short. Machine learning people do love coming up with goofy acronyms. In this case, the agent will purposefully add some noise to the example trajectories to generate instances where it has veered off course a bit, and then a human has to go and annotate what it should do in those instances. This makes for a more robust type of imitation learning, but of course the downside is it's very tedious to have humans go and label all that data. Despite that, imitation learning has been used to do some pretty cool stuff. For example, this paper shows a human demonstrating to a robot how to catch a ball in a cup. And you can see that at first when the robot tries to imitate that, it's not successful, but over time it gets closer and closer, and finally, after 100 trials, is able to catch the ball in the cup. I also found this example of a robot dog learning to walk by imitating a real dog, and a surgery robot learning to suture by imitating human footage. In contrast to imitation learning, inverse reinforcement learning, or inverse RL, refers to methods that rather try to learn what the reward function is supposed to be. It's kind of like observing some behavior, and rather than trying to mindlessly follow it, actually try to figure out what the underlying goal is, and what outcomes are good or bad. I didn't find as many cool demos for inverse RL as for imitation learning, but one paper showed a method called inverse Q learning, which focuses on learning the Q function from expert demonstration and subsequently the reward function. The agent seems to be able to play Atari games, perform movement in Minecraft, control a simulated robot arm, etc., just from watching 20 to 30 expert demos. Also pretty cool. So there we have it. To recap this video, we first went through what a Markov decision process is, and then applied it to a grid maze example. We solved this grid maze example with a Monte Carlo method, and then showed how we can improve upon that with temporal difference using a method called Q-learning. Then we added on a neural network to Q-learning, making deep Q networks in order to learn lunar lander, now going from discrete to continuous state spaces. After that, we went through the math of policy gradients, and with policy gradients, we were also able to handle continuous action spaces, not just continuous state spaces. Then we talked about how aspects of reinforcement learning show correlations to neuroscience and certain parts of the brain. And finally, we discussed the current shortcomings of RL and what directions of future research could help with it. I hope you found value from this video. If you did, and you're interested in more videos on related topics of AI and robotics, consider supporting the channel on Patreon, where I'll put behind-the-scenes clips and previews, link in description. I hope you learned a lot about reinforcement learning. I hope you found the field fascinating, and I hope one day we will have robots that can tie our shoes and fold our clothes. With that being said, see you next time.